Okay, I'm going to give you a quick run through of what we did today in class in case you were absent. Enthalpy of combustion is given the symbol delta H sub C for combustion, the heat released upon the complete combustion of 1 mole of a substance. An example, this is the burning of ethanol. Anytime you burn something, oxygen is going to be a reactant. Of course, burning is another way of saying combustion. For an alcohol or a hydrocarbon, the products are always the same, carbon dioxide and water. Okay, now the delta H for this reaction we would call the enthalpy of combustion. Okay. Now we can look up the enthalpy of combustion from table 13 of the IB data booklet. So let's take a look at that. This is table 13, and we simply have various substances listed here with the enthalpy of combustions here. The enthalpy of combustion, again, is kilojoules per mole. So this is the amount of energy that's released when we burn 1 mole of a substance. The one that we were just looking at, ethanol, is down here. It's a negative 1367 kilojoules per mole. So we can put that into the value here. That's the amount of energy released in the burning of 1 mole of ethanol. Little note here, the little degree symbol that we have on the delta H, and you'll see that a lot, means standard conditions. Standard conditions is a set temperature, pressure, and concentration. The temperature is 25 degrees Celsius or 298 Kelvin. The atmospheric, or the pressure would be 1,000 kilopascals. That's a unit of pressure. It's very close to standard pressure. And if the reaction took place in solution, all the solutions would have a concentration of 1 molar. Now, for a combustion reaction, that isn't pertinent. Combustion doesn't take place in solution. But those are, anytime you see that little degree symbol, that means that these are the standard conditions. By and large, you can just ignore it. But that's what it means. Okay, I did a lab demo where I burnt methanol and then use calorimetry to calculate the amount of heat that was released by the ethanol. So this was the setup. I used a pop can with water in it and an alcohol burner that had methanol in it, and then measured the change in temperature of the water. The data collection and calculations were done in class, and this is a picture of one of the periods data that we collected. So in the alcohol burner, we took the mass, or I took the mass beforehand, 239.90 grams. And then the mass that was in the pop can, or the calorimeter, was 199.54 grams. And the initial temperature of the water was 22.6 degrees Celsius. Then I lit the alcohol burner, warmed up the water, and the water warmed up to 90.8 degrees Celsius. And then I blew out the alcohol burner and took its mass, and it had lost 4.10 grams. It went down to 235.80 grams. And then I looked at I calculated the delta T. So remember, it's always final minus initial, and so that gives us 68.2 degrees Celsius for our delta T, and that's for the water. And then I went ahead and calculated the mass of the methanol that reacted. So in order to warm the water up from 22 degrees to 90 degrees, it took 4.10 grams of methanol. And I will need that to be converted to moles, and so I just stopped and did it at this point. So the molar mass of methanol is 32.05 grams, and so it was 0.128 moles of methanol that reacted. And then it's just a calorimetry problem, just like we did last week. First looking at the water, so the specific heat of the water, the mass of the water, the change in temperature of the water gives us 56.9 kilojoules. So that's the amount of energy that the water absorbed, which is equal in magnitude, opposite in sign, to the amount of heat that the methanol released. And then to calculate the enthalpy of combustion, it's going to be the heat released by the methanol divided by the number of moles of the methanol, and that would give us a negative 445, that should say kilojoules. Change that to kilojoules per mole. Kilojoules per mole. Okay, and then we looked at standard enthalpies of formation, and that's given the symbol delta H, F sub F for formation. And it is the change in enthalpy that accompanies the formation of 1 mole of a compound from its constituent elements. Constituent just means the elements from which it's composed. This is also known as, aka also known as, heat of formation, and that's the title of your homework assignment, heat of formation. Now, of key importance here in this definition is that it's the formation of 1 mole of a compound. Excuse me. Example, if we were to look at this equation, we see, well, that it forms a compound, water, but it's not 1 mole. And so we need to fix this equation if we want it to represent a heat of formation equation. So I would divide everything by 2 to make it so that when we look at our balanced equation, it's 1 mole of a compound. So now we can refer to that as being the enthalpy of formation. So the amount of energy associated to forming 1 mole of water, we can look up. Okay. Now note, for an element, the enthalpy of formation is 0, as you'll see. This is a table of enthalpies of formation, and you can see that many of them are zeros. And what do they all have in common? Like I just said, if you were to look at the substance, it's going to be an element. So chlorine is a diatomic element, calcium, hydrogen, potassium, these are all zeros. So you never have to look up the enthalpy of formation of an element. It's always going to be 0. Couple of things. This is not from the IB data booklet. This is another table that is just a little bit easier to use for our purposes. Though IB does have an enthalpy value or enthalpy of formation table that you could look up, but it's a little problematic for what we're doing, so we're going to be using this table. Also, we're going to be rounding the values from this table to 1 decimal place. As you can see, some of them go to 2 decimal places, some go to 3 decimal places, some go to just 1 decimal place. So we're just going to be universal on this, round all values to 1 decimal place. Okay, that enthalpy of formation equation that we derived a minute ago, we can now look up the value for liquid water. So it's right here, liquid water. And so the enthalpy of formation is a negative 285.8. So again, we rounded to 1 decimal place. Now be careful, this is liquid water, right below it is gaseous water, so they have different values. Okay, we did a little bit of practice writing balanced enthalpy of formation equations, and the main idea here is when we write our balanced equation, we have to make sure that the compound that forms the coefficient is 1. So we're a little handicapped when we go to balance it. So for example, when we try to balance this equation, I can't just multiply the sodium chloride by 2 to balance out the chlorines and then put a 2 in front of the sodium, because I need to have the compound that forms be a 1. So to balance that, this would be a 1/2 Cl2. So now it's balanced. And so and then when we look up the enthalpy of formation values on the table, that's what we would get. And so that's what we did for each one of these. I'll just fast forward through it. So all I'm doing here is balancing each one of these reactions so that it's only 1 mole of the substance it forms, and then we can look up each one of those substances on the enthalpy of formation table and determine what the value would be. So all of these values that are on the right, I simply looked up on that table that we just looked at. Enthalpy of formation is usually negative, but you can see on the last one here, it's positive. Sometimes it's positive. Okay, now this is the most important thing. We're going to be using the enthalpy of formation to calculate the enthalpy of a chemical reaction. So let's look at this little triangle, energy triangle here. If the one thing that we know the reactants and products have in common is that they are made up of the same elements. we just have to balance it so that they agree with one another. But the elements that the reactants have will be exactly the same elements that the products have. So what we can do is we can simply look at the formation of all the reactants from the elements that make them up and do the same thing for the products. So this arrow here would be the enthalpy of formation of all the reactants, and this arrow here would be the enthalpy of formation of all the products. Now remember, last week we talked about the conservation of energy, and when we looked at Hess's law, we walked through an energy diagram that looks much like this. So notice that there are two paths that we can take to get to the products. We can go from the elements directly to the products, and that would be the enthalpy of formation of the products. Or we could go the elements to the reactants, that would be the enthalpy of formation of the reactants plus the enthalpy of the reaction itself. So I can write an expression to represent that. Now you might not be familiar with this symbol sigma. It means to sum or to add together. So what we're looking at here, and the way that I would read this, is the sum of the enthalpy of formation of the reactants, and that's this arrow here. So all of the reactants, whatever they might be, we are going to add together all of the enthalpy of formation. And we're going to get those values right from the enthalpy of formation table. And then if we add the enthalpy of this reaction, whatever it might be, the sum of those two, adding those together, would give us the sum of the enthalpy of formation of the products here. And another way of looking at this is the counterclockwise delta H's is going to be equal, the clockwise delta H's are going to be equal to the counterclockwise. So this arrow and this arrow go clockwise. So if we add those two together, we'll have exactly the same amount of energy associated with that path as we would have going from this path, which is the counterclockwise. Now, the enthalpy of formation of the products and the reactants, we can look those up. What we're interested in is the delta H of a particular chemical reaction. So I'm going to rearrange this. So all I did was subtract delta H of the enthalpy of formation of the reactants for both sides, and we get this expression. This is the main expression we're going to be needing to use. So the enthalpy of a reaction is going to be equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. Okay, so let's do a couple of practice problems, and hopefully this will fall into place. Okay, so this is a practice problem. Okay, so what we're going to be interested in is the enthalpy of formation of all the compounds. Water is a compound, calcium hydroxide is a compound, but calcium is not, it's an element. Hydrogen is not, it's an element. So the enthalpy, let me just kind of put that, okay. So it's going to be the enthalpy, the sum of the enthalpy of formation of the products, and that's what's in the brackets here, minus the sum of the enthalpy of formation of the reactants, and that's what's in the brackets here. And above each one of the numbers that are listed, I've written the compound from which it's in reference to. So if you were to look up the calcium hydroxide on the enthalpy of formation table, it's a negative 986.1. Hydrogen is 0. Now remember, the equation that we just looked at and boxed was it's the enthalpy of formation of the products minus the enthalpy of formation of the reactants. So inside the brackets, we're simply adding together all the enthalpy of formations. So for the products, these are enthalpy of formations, and we're simply adding them together. And then on the reactants, calcium again is 0. Now water, when you look up the enthalpy of formation of water, it's negative 285.8, but that's per 1 mole. In the reaction that we're interested in, we have 2 moles. So we need to multiply that number by 2. So when you do these problems, you always need to multiply the enthalpy of formation values that you get from the enthalpy of formation table by whatever coefficient we have in the equation we're interested in. Now when you type this into your calculator, you don't need to put in all these brackets and parentheses. Let me show you the simple way of doing it. So on your calculator, type in, so get your calculator. I'll wait. Got it? Okay, good. Type in 986.1 and then hit the change sign key. On the calculators that we use in class, it's right next to the equal sign in the lower right. So just make it a negative 986.1. And then we can see what we're going to eventually do is subtract a negative number. Well, of course, subtracting a negative number is adding it. So all I would do would be to take the negative 986.1 plus 2 times 285.8. And that would give me a negative 414.5 kilojoules. Now the unit for enthalpies of formation is kilojoules per mole, but the coefficients that we're multiplying by, whether it's a 1 or a 2 or whatever it might be, that number means moles. And so even though when you looked up this value, let's just look at the water here, and it would say it's negative 285.8 kilojoules per mole, the moles cancel out. And so that's why when we write the amount of energy associated with a particular chemical reaction, we don't include moles. It's not that it's wrong if you do it, it's just you don't need it. All right, one more practice problem. And I'll tell you, I'll stop it here. Well, no, I'll finish it. Why don't you pause the video and see if you can do this one yourself. And come back in 3, 2, 1, and it is. So again, the sum of the enthalpy of formation of the products, and so it would be 2 times the enthalpy of formation of the hydrogen fluoride, that's this here, plus 1 times the enthalpy of formation of the sulfur hexafluoride, it's this number here, and then subtract from that the sum of the enthalpy of formation of the reactants, which we have here, and that will give you negative 1,742.1. And that's it. That's how you solve those problems. I know I went really fast, but I did this in class. So hopefully, I think there was only one person absent, but I also had another person that requested this. So hopefully this will be helpful. We'll have a chance to practice these a little bit more later on. But for now, that is the end of notes.